Around our planet, there's an invisible magnetic shield that blocks solar radiation. But it isn't spread evenly. One patch is thinner and it has a name – the South Atlantic Anomaly. On the ground, we're fine. Up in orbit, satellites get glitchy as they fly through charged particle storms. And lately, that weak spot looks like it's changing shape. It's spreading out, and some maps even show it splitting into two. So why is that happening and what does it mean? Well, to understand the weak spot, we have to go deep below to the core of the issue and the planet. Around 1,800 miles down, Earth's outer core is a boiling ocean of molten iron and nickel. There, the temperature can rise to more than 10,000 degrees Fahrenheit. As that liquid metal moves, it generates electric currents, and those currents create our magnetic field. Now, without the field, the sun's charged particles would slam straight into our atmosphere and start stripping it away. But this magnetic field isn't a smooth, perfect bubble. It's lopsided and tilted. It's constantly shifting. Beneath Africa, some magnetic lines bend the wrong way, back toward Earth instead of out into space. Scientists call these reverse flux patches, and they weaken the field above them. Right over that weak spot is the SAA, the South Atlantic Anomaly I mentioned earlier, and it's changing fast enough that we can watch it shift over just a decade. Scientists know this because of an ESA mission called SWARM. It's 3 satellites constantly, swarming, and mapping Earth's magnetic field in detail. Their maps show that the anomaly has been spreading since the mid-2010s. It's getting weaker and starting to look like it's splitting in two. Now, back down here, we're protected by the atmosphere, but we are still affected indirectly if satellites start acting weird. Most of the satellites we rely on are in low Earth orbit, a few hundred miles up. Over the SAA, the radiation belts droop closer to Earth than usual, so when a satellite passes through, it's like driving through a stretch of space that's far more charged than normal. A single burst of particles can flip tiny bits inside a computer chip. It can corrupt a sensor for a moment or trigger a reset. It can force the satellite into safe mode, where it shuts down anything sensitive to survive. Many satellites cross the SAA multiple times a day, which means each pass is another roll of the dice. Even Hubble has to respect it. Hubble is one of the most famous space telescopes that's been taking those insanely sharp pictures of galaxies, nebula, and weird deep space stuff for decades. But when it's about to fly through the South Atlantic Anomaly, it basically goes, no. It stops certain observations and shuts down its most sensitive detectors until it's in the clear again. The satellite is too valuable, and it's not worth taking chances and losing it. Which is exactly what happened to a high-tech Japanese satellite. In 2016, Japan launched Hitomi, a next-gen X-ray space telescope built to study the hottest and craziest objects in the universe, stuff like exploding stars and monster black holes. It was supposed to run for years. Instead, a problem that showed up when it was passing through the SAA kicked off a cascade of attitude control failures. The spacecraft ended up spinning, breaking apart, and the whole mission was lost just weeks after launch. That's not a glitch. That's a multi-year science plan worth billions of dollars lost in just a month. So why does SAA seem to be growing, and why would it split into two? Deep under Africa, Earth's core is like a giant pot of liquid metal. The swirls can change shape over time. Imagine you're holding a strong magnet under a table, and on top of the table there's a thin metal sheet. If you slide the magnet around underneath, the metal above shifts too. If you use one magnet, you get one dent. If you move it or add another magnet nearby, the dent stretches or splits into two. The moving liquid iron deep below acts like shifting magnets. When the flow pattern changes, it creates weak spots in the magnetic field. If one weak spot spreads underground, the dip above it spreads too. If two weak spots form close to each other, that single sag at the surface can split into two dents right next to each other. And that's where this stops being cool Earth science and starts being a problem. Because if the magnetic field can rearrange itself that much in a decade, well, anything we rely on in orbit has to deal with it. But is the South Atlantic anomaly just one local weak spot we have to work around? Or could it be an early hint of something much bigger, like a pole reversal? You see, Earth's magnetic poles are not locked in place forever. North and South have swapped many times before. Magnetic North can drift, weaken, and eventually trade places with magnetic South. Wait, what does that actually mean? Well, it means those football fans who are gathering in the North Stand now have to start cheering from across. But, jokes aside, the planet is not flipping around or becoming the upside-down world. The liquid iron shifts its flow pattern, and the whole magnetic layout reshuffles. Just like every other natural process, it doesn't happen all of a sudden. The field can weaken first, it can break into uneven patches, it can look messy for a while before it settles again. That problematic stage is what would matter most for satellites. Because we know this happened before. When hot lava cools into rock, tiny bits of metal inside line up with Earth's magnetic field and get stuck pointing that same way. Much later, scientists can read that direction like a compass arrow trapped in stone. One famous case is the Lachamps event about 41,000 years ago. Hey, I wasn't around then. But for a while, Earth's magnetic field got much weaker. Then it partly flipped, and then it bounced back. The simplest idea is that the liquid iron deep inside Earth started flowing in a different, unpredictable way for a while. So the magnetic field got scrambled. A pole reversal is the biggest version of this scramble. The South Atlantic anomaly is a smaller, local version. Both happen because the liquid iron flow deep inside can change. The SAA does not mean a reversal is definitely coming. It just shows the magnetic field can get uneven when the stuff underneath shifts. While the anomaly is changing, there's another space problem that can hit way beyond that one spot in the Atlantic: geomagnetic storms. The Sun sometimes launches a huge cloud of superhot gas with its own magnetic field. It's called a coronal mass ejection, or CME. Some of these clouds race outward at over 1,000,000 miles per hour. If one of them is aimed at Earth, it slams into our magnetic shield and shakes it. That shaking dumps extra energy into the space around Earth. It scrambles radio signals, messes with GPS accuracy for a while, and, in extreme cases, even pushes electric currents into long power lines on the ground. Oh, and they also cause breathtaking auroras. Back in March 1989, a major geomagnetic storm triggered a Quebec blackout that left 6 million people in the dark for hours. Another example was in May 2024, when a strong geomagnetic storm disrupted certain satellite and radio signals, forced some airlines to adjust routes, and pushed auroras much farther south than usual. Solar storms don't hit at the same strength all the time. The Sun goes through an activity cycle that lasts about 11 years. During the busiest phase, it fires off more flares and more giant clouds of charged particles, so strong geomagnetic storms become more likely. Right now, we're in one of those busier stretches. So the odds of rough space weather are higher than they were a few years ago. But the bigger reason it feels scarier is how modern life works. We lean on satellites and power grids more than ever. So a storm that used to be a cool aurora night can now mean signal glitches, GPS hiccups, rerouted flights, grid strain, and a lot of expensive fixing. Wow, nobody could have predicted this. Thousands of Airbus planes had to be grounded at once. Was it a technical glitch, a construction mistake, a human error? Not at all. It happened because the plane's computers might get messed up by something coming straight from space, something that could cause a terrible disaster and claim hundreds of lives. Now the thing is, our sun is always shooting out charged particles, like a powerful invisible wind. And on top of that, we're constantly getting hit by even stronger particles from outside our solar system. Those are called cosmic rays. We never feel them, but they're always there. Most days they're harmless. But sometimes the sun fires off a massive burst, a solar storm. And that stuff can seriously mess with electronics. It's also what triggers those insanely bright auroras. Now, because of this risk, Airbus checked around 6,000 planes. About 5,000 of them needed a simple software update. But around 900 older planes needed a whole new computer. According to Airbus, radiation from the sun might have corrupted data that's essential for flight control. And this issue could have affected many A320 aircraft already in service. The main problem is a piece of software that calculates the plane's elevation. If high-energy particles hit the computer at the wrong moment, the hardware can glitch, and that glitch becomes a software error. You see, when planes fly high, the air is thinner, so more space particles get through. If one of those particles hits a microchip, it can flip a tiny bit. A 0 becomes a 1, or a 1 becomes a 0. That tiny flip is called a single-event upset, and it can make electronics act weird. You can probably imagine the catastrophic outcome an altitude-related mistake can lead to. Airbus planes are finally getting back to normal after the company rushed out a software fix, which was way faster than anyone expected. By the way, the warning itself came after a JetBlue flight ran into trouble mid-air when a solar flare may have messed with its flight controls. That JetBlue plane was flying from Cancun to New Jersey when something suddenly went wrong. The jet dropped sharply. It was fast enough that people were thrown around the cabin. Some passengers hit the ceiling. Around 15 to 20 people ended up in hospitals. At 2:19 p.m., the pilots made an emergency landing in Tampa. Medical teams immediately rushed on board. JetBlue pulled the plane from service immediately, and the FAA is now digging into what exactly happened. In any case, these days we rely a lot on watching the sun. There are satellites in space right now whose only job is to track solar tantrums and warn us before they cause trouble. Luckily, we're finally heading toward a calmer period of the sun's cycle, but it never truly quiets down. Even when our star seems calm, it's still firing particles at us non-stop. And recently, scientists from several countries found something hidden in ancient tree rings, a huge jump in radiocarbon dating from about 12,350 BCE, right near the end of the last ice age. For years, no one could tell how strong this spike really was because there was no good way to model it. Now, with a new climate chemistry model, researchers have finally figured out that this thing was the most powerful solar particle storm ever found. Nothing else in the record even comes close. The team built a special model. It's designed to recreate how the atmosphere behaved during glacial times, letting them study ancient solar storms. And when they tested the model on the newly discovered event, they found it was even stronger than the famous AD 775 storm, which used to be considered the biggest one on record. Compared to a strong solar storm from 2005, the Ice Age event was hundreds of times more intense. Other big historical storms did happen long ago, around 994 CE, 663 BCE, 5259 BCE, and 7176 BCE. Hey, I wasn't around then. But none of them reached this level. The researchers also checked the model using wood found in the French Alps that dates back around 14,300 years, so the timeline lines up. Solar particle storms don't happen often, but when they do, they blast Earth with high-energy particles that can change the atmosphere and leave clear marks in tree rings. Even the famous Carrington event of 1859, which knocked out telegraph lines around the world, was actually a different kind of solar outburst. What makes this new discovery stand out is that it's the only known extreme solar particle event from before the last 12,000 years of warm climate. Until now, scientists could only look for such storms inside that window. But with this new model, the scientists were finally able to figure out how strong this ancient solar outburst really was, when it hit, and what it might have done to Earth. The model now works for both warm periods and for the cold, icy world that existed before it. That's a big step forward for studying old radiocarbon spikes. The team focused on how solar particle storms can pump huge amounts of extra radiocarbon into the atmosphere. Normally, this type of carbon forms when cosmic rays hit our air. But during one of these extreme storms, the amount shoots up fast, and trees trap that sudden jump inside their rings, which basically creates a time stamp that survives for thousands of years. These sharp spikes, known as Miyake events, have already helped scientists date things like Viking settlements in North America and early farming communities in Greece. This ancient blast sets a new upper limit for what our star can do, and it's alarming. Knowing the size of the event is crucial. A storm of that scale today could threaten satellites, mess with communication systems, and overload power grids. It gives researchers a clearer picture of the most extreme kind of space weather our planet might ever face, and what it could mean for modern life. Now luckily, Earth is wrapped in a kind of invisible shield that blocks most of the dangerous particles the Sun throws at us. For almost 10 years, 4 small NASA spacecraft, called the MMS mission, have been flying right along the edge of that shield, watching how it bends, snaps, and reacts to the Sun's magnetic forces. Now during one of those passes, the probes caught something nobody expected – a sharp twisting bend in Earth's magnetic field. Scientists call this kind of shape a switchback. They've seen them near the Sun before, but never this close to Earth. Finding one in our space neighborhood is kind of like spotting a wave curling backwards in the middle of a calm lake. This switchback showed up in the magnetosheath, the turbulent zone where the solar wind slams into Earth's shield and gets pushed aside. Inside the twist, the probes picked up fast, energetic electrons that came from Earth's own magnetic field. They were mixed with particles from the Sun, and everything was spinning together inside this strange structure. The spacecraft recorded how the magnetic field flipped, how fast the particles were moving, and how the whole thing behaved. The twist seemed to come from a process called magnetic reconnection, where magnetic fields from the Sun and Earth snap together and release a burst of energy. These bursts can set off bright auroras. But the big ones can also knock out satellites or mess with power grids. The MMS probes will keep flying through the area, hunting for more twists and bursts, trying to pin down what causes them and which ones are strong enough to mess with our technology on the ground. The problem is that tiny magnetic snap might let radiation push far deeper into our atmosphere. And now, scientists are starting to connect the dots. Strange aviation glitches, signs of ancient megastorms buried in old trees, and now a fresh crack in our magnetosphere. Together, they paint a worrying picture. We depend on calm space weather for everything – planes in the sky, GPS, satellites, even the power running through our homes. The Airbus grounding might end up looking like a gentle warning, the first hint that something much bigger could be building out in space. The protective shield of our planet decays and eventually fails. So do our satellites. First, communication satellites in the highest orbits go down. Next, astronauts in low Earth orbit can no longer contact their mission control center. And finally, hazardous, relentless cosmic rays start bombarding everything on Earth, causing havoc and devastation. Are these the terrifying consequences of the planet's magnetic field reversal we're going to face? Right now, as you're watching this video, Earth's north magnetic pole is extremely out of whack. It's so serious that scientists will have to update the global magnetic field model released a mere 4 years ago. Does it all mean that the magnetic pole of our planet will flip soon? Well, be patient, we'll figure it out a bit later. You see, the magnetic pole is moving quite erratically from the Canadian Arctic towards Siberia, and these movements are very unpredictable. But it's normal for the pole to be moving. There are long-term records from London and Paris that prove that the North Magnetic Pole moves randomly around the rotational North Pole over periods of several hundred years. But the most astonishing thing about its movement is that it's speeding up. Around the mid-1990s, the magnetic pole unexpectedly accelerated from a bit over 9 miles to 34 miles a year. And recently, the pole crossed the international date line, moving toward the eastern hemisphere. The European Space Agency launched extremely accurate magnetic field satellites in 2013. Thanks to them, researchers have superb data they can use not only to make magnetic field maps, but also to update them every 6 to 12 months. That's how they were able to notice that the core field was weakening too. It might be a sign that the planet's magnetic field is about to flip. To understand this process better, we need to figure out how the core field works. Let's say we've got a bar magnet that runs through the center of our planet and has a north and a south pole. This magnet is incredibly strong, representing about 75% of the intensity of our planet's magnetic field at the surface. Our bar magnet is not only moving, but is also getting weaker, by about 7% every century. Admittedly, this bar isn't the perfect representation of the core field. It's more like electric currents generating Earth's magnetic field. Still, this model makes it easier to see what's happening to our planet now. The magnetic field of our planet plays an important role in protecting us from dangerous radiation and geomagnetic activity, which is the product of the interaction between the solar wind and Earth's magnetosphere. Earth's magnetic field also moves. Scientists have been studying and tracking the movement of the magnetic poles for hundreds of years. The historical motions of these poles indicates changes in the global geometry of the magnetic field of our planet, and they may point to the beginning of the field reversal too. That's what the flip between the north and south magnetic poles is sometimes called. You see, if the north magnetic pole moves a bit, it isn't a big deal. But a complete reversal might have a serious impact on the climate of our planet, as well as modern technology. Luckily, such flips don't happen overnight. The entire process stretches over thousands of years. Plus, even though the magnetic pole weakens during a pole reversal, it doesn't disappear completely. So those scary events from the beginning of the video aren't likely to happen to us. The magnetosphere will continue protecting the planet from cosmic rays and charged solar particles, even though there might be some amount of particulate radiation that will make it to Earth's surface. Magnetic fields are generated by moving electric charges. If some material allows these charges to easily move in it, it's called a conductor. Metal is a great conductor, and we often use it to transfer electric currents from one place to another. In this case, the electric current is negative charges called electrons moving through the metal. The current is what generates a magnetic field. Earth has a liquid iron core. In other words, there are layers and layers of conducting material inside our planet. Currents of charges are constantly moving through the core, and the liquid metal is also moving and circulating there, generating the magnetic field. This magnetic field, in turn, produces something resembling a bubble around the planet. It's called the magnetosphere, and it's located above the uppermost part of the atmosphere. This layer shields and deflects high-energy cosmic radiation, which otherwise would be extremely dangerous to people and other forms of life on Earth. The magnetosphere also interacts with the ionosphere, the layer of our planet's atmosphere containing loads of ions and free electrons and capable of reflecting radio waves. The interaction between these two layers and the magnetized solar winds is what scientists call space weather. The solar wind is normally mild, and there's no space weather whatsoever. But sometimes, the sun starts shedding gargantuan magnetized clouds of gas that can accelerate to incredible speeds. They're called coronal mass ejections, or CMEs. They're ejected from the sun over the course of several hours. CMEs usually look like giant twisted ropes and can occur spontaneously. Their frequency varies according to the 11-year-long solar cycle. For example, at a solar minimum, you can observe one ejection per day, and when the sun is in its most active phase, there might be 3 CMAs per day. Coronal mass ejections disrupt the calm flow of the solar wind and cause serious disturbances that can damage stuff both in space near Earth, like satellites, and on the planet's surface. If coronal mass ejections make it to Earth, their interaction with the magnetosphere generates geomagnetic storms. Those can trigger auroras, happening when a stream of energized particles hits the atmosphere and lights up. And then there are also solar flares. They develop more rapidly and with much more energy than coronal mass ejections. Solar flares often occur soon after coronal mass ejections. The most powerful volcanic eruptions pale in comparison to solar flares that release 10 million times more energy. Within a few minutes, one solar flare can give out billions of tons of charged particles. Solar flares are also insanely hot, with temperatures reaching several million degrees Fahrenheit. Astronomers believe that such bursts of solar radiation happen when the sun's magnetic field gets twisted in some regions. At one moment, all the pent-up energy is released. The star sends out light and particles, mostly electrons and protons. Most solar flares last for minutes, but some continue for hours. A powerful solar storm can potentially cause a devastating global blackout on Earth. If not for the Earth's magnetosphere, the effects of the sun's activity would be much more devastating. Luckily, the magnetosphere deflects most of the solar material hurtling towards our planet from our star at a speed of over 1 million miles per hour. But even so, during space weather events, there's a lot of hazardous radiation near Earth. It can potentially harm astronauts and spacecraft. Plus, space weather can damage large conducting systems, for example, pipelines and power grids, by overloading currents running inside them. Scientists regularly map and track the overall orientation and shape of our planet's magnetic field. To do it, they use local measurements of the field's orientation and magnitude. That's why they've been able to conclude that the location of the North Magnetic Pole has moved by almost 600 miles since the first measurements were taken in 1831. The magnetic field of our planet reverses on a timescale varying between 100,000 to 1 million years. One can tell how often it happens by looking at volcanic rocks at the bottom of the ocean. They capture the orientation and strength of Earth's magnetic field at the time of their creation. So, dating those rocks gives us a good picture of how our planet's magnetic field has evolved over time. From a geological point of view, field reversals happen quite fast, but they are extremely slow from a human perspective. A complete reversal normally takes a couple of thousand years, but during this time, the orientation of the magnetosphere may shift, exposing more of Earth to cosmic radiation. Such events tend to change the concentration of ozone in the atmosphere. In any case, scientists can't say for sure when the next field reversal will happen, but they keep mapping and tracking the movement of our planet's magnetic north. By the way, the Earth isn't the only planet with a magnetic field. Gas giants, like Jupiter, also have a conducting metallic hydrogen layer that generates their magnetic fields. Jupiter's internal magnetic field prevents the solar wind from interacting directly with the planet's atmosphere.
A powerful burst of gamma radiation lasted a mere half-second, but it released an enormous amount of energy. It was more than our sun would produce in 10 billion years. This brief flash lit up the whole sky. Afterward, a much softer and more long-lasting glow replaced it. Astronomers examined the phenomenon with X-ray, radio, optical, and infrared waves. It turned out that people had finally seen a newborn magnetar for the first time ever. It was likely formed after two neutron stars had merged. It resulted in a kilonova, one of the brightest and largest stellar blasts. Its light finally reached our planet on May 22, 2020. Imagine a massive star, at least 5 times the mass of our sun, reaching the end of its life. It might be because it's run out of its nuclear fuel. If it happens, the star starts to cool off. The pressure inside drops, and the gravity starts to squeeze inward. And then, more than 1 million times the mass of our planet collapses within 15 seconds. It happens so fast that an enormous shock wave causes the outer part of the star to blow up. It produces a blinding burst of light. This powerful blast is called a supernova. What's left behind is an incredibly dense core with a huge cloud of hot gas, called a nebula, expanding around it. If the star has been massive enough, more than 10 times the size of the sun, it's likely to turn into a black hole. If not, it turns into a neutron star. It's basically a giant nucleus, the central part of an atom. These stars are mostly made up of neutrons and are rarely larger than 20 miles across. For comparison, our Sun is almost 865,000 miles across, which is 109 Earths put side by side. But don't let this relatively tiny size fool you. Any neutron star is at least 1.5 times heavier than our Sun and has an intense magnetic field. If you scooped just a teaspoon of this star's insides, this matter would weigh more than 1 billion tons. It's so dense that it makes neutron stars some of the most extreme objects people know about. The next stop is the black hole itself. When two neutron stars merge, they most often create a new, much heavier one. Within milliseconds, or even less, this star collapses into a black hole. But the astronomers who examined the flash of light recorded in March think there might be another outcome. They're almost sure they saw something never observed before: the birth of a magnetar. That's a rare form of a neutron star with an ultra-strong magnetic field. It's 1,000 trillion times stronger than our planet's. This field is also so powerful, it heats the star's surface up to 18 million degrees Fahrenheit. To put it simply, magnetars are the most powerful magnets in the universe. Their magnetic fields can seriously mess with the neighborhood. Atoms, unlucky enough to get close to such a star, get stretched into pencil-thin lines. If you somehow found yourself several hundred miles away from a magnetar, it would end badly for you. The magnetic field would first disrupt your bioelectricity. It means that your nerve impulses wouldn't work anymore. Even your molecules would change under the influence of the star's field. In the end, you'd pretty much vanish. If a magnetar flew within 100,000 miles from our planet, it would wipe out all the data on every single credit card in the world.
Did you know that the moon is rusting? No, not rustic, rusting. Well, that sounds impossible because rust needs oxygen, and the moon, well, it doesn't have it. Or so we thought. Apparently, Earth is leaking its air, and it's marinating the moon. It might have been like that for billions of years. What does this mean? And why do scientists say it's great news for a future lunar base? Well, let's find out. A few years ago, the Indian Space Research Organization sent a probe called Chandrayaan-1 to orbit the moon. Its mission was to take some nice pictures, but it also was carrying a NASA-built instrument designed to chemically map the surface. The readings came back showing something scientists didn't expect on the moon: hematite. It's an iron oxide, or in plain words, rust. It's the same red, rusty material that eats through your garden fence or a forgotten bicycle chain. Finding rust on Earth is normal because our planet is wet and airy. You need a strict recipe to make it happen. You need iron, you need water, and you need oxygen. The moon already has the first ingredient for rust because its surface is rich in iron from billions of years of asteroid impacts. But the other two ingredients are missing. There is no atmosphere to provide oxygen, and there is no liquid water gathering on the surface. But it goes beyond that. Space actually hates rust. The sun constantly blasts the moon with the solar wind, a stream of fast particles made mostly of hydrogen. Well, these particles tend to strip oxygen away from rocks instead of adding it. All of that makes it obvious why hematite doesn't belong anywhere near our satellite. But these results don't lie. The presence of hematite means that somehow, despite the vacuum and the sun's particle stream, the moon is getting a steady supply of oxygen. It's not coming from deep space or the lunar core. Also, the rust isn't spread evenly. The data showed that the hematite is more concentrated on the side of the moon that faces Earth. The far side is mostly clean. Now, the only oxidizer close enough to do the job is Earth. We learned at school that Earth's atmosphere ends at the Kármán line, about 62 miles up. That's where space officially begins. But that's just the thick part. In reality, Earth is wrapped in a gigantic invisible cloud of hydrogen called the geocorona. It's enormous. It glows in ultraviolet light, and it stretches almost 400,000 miles into space. That's farther than the moon's orbit. This means that despite being very far away, the Moon is still within the outer edges of Earth's atmosphere. If you were standing on the Moon, looking back at Earth with a telescope that can see ultraviolet hydrogen, Earth wouldn't look like a blue marble. It would look like it's wearing a huge, fuzzy, glowing halo. Now, when we picture Earth and the Moon, we imagine a huge, clean gap between them. Two worlds separated by nothing. But that nothing isn't actually empty. The two are already connected by gravity, tugging on each other nonstop. But there's another kind of connection most people never think about. Earth is surrounded by an invisible force called a magnetic field. It's created deep inside the planet and stretches far out into space. We don't see it, but it's the reason compasses work and the sun doesn't strip our atmosphere away. This magnetic field doesn't just stop at Earth's surface. It doesn't sit there like a perfect bubble either. The solar wind pushes on it non-stop, stretching it out behind Earth into a long magnetic tail that reaches hundreds of thousands of miles into space, like a tail trailing behind a moving comet. That tail is how Earth's oxygen ends up on the Moon. The sun slams into Earth's upper atmosphere, knocking oxygen and nitrogen atoms loose and turning them into charged particles. Normally, they'd drift off into space. But because they're charged, Earth's magnetic field grabs them and sends them backward, down the magnetic tail. Most of the time, the Moon is off to the side doing its own thing. But once a month, right around the full moon, it slides straight into Earth's magnetic ponytail. Inside that tail, Earth blocks the harsh solar wind and gives the Moon a few days of calm. But it's still moving straight through particles leaking from Earth. Those particles collide with the surface and react with the iron in the soil. Repeat that long enough, and it adds up. Earth loses tiny traces of its air, and the Moon quietly collects them using its weak gravity like a slow, patient net. It's like driving behind a dirty truck. Dirt flies off of it, but you don't really notice until it starts sticking to your windshield. The same thing happens on the Moon, except, no windshield. We actually have proof of this happening in real time. A Japanese probe called Kaguya was hanging out in lunar orbit, and its sensors spiked when the Moon passed through Earth's magnetic tail. It detected a surge of high-energy oxygen ions. Scientists call it the Earth wind. It acts like the solar wind, except instead of being hot particles from a star, it's made from leftovers of our own atmosphere. And this suddenly makes the Moon part of a much bigger story. Scientists think this kind of atmospheric escape can help explain what happened to planets like Mars. The red planet doesn't have a global magnetic field today, but long ago it probably did. When that shield failed, its atmosphere had a much easier time leaking away. Studying Earth and the Moon is like watching a version of that process on replay, just in slow motion. And it's not unique. Near the edge of the solar system, Pluto's thin atmosphere is slowly being stolen by its moon Charon. Ooh, larceny in space. Pluto's gravity is so weak that its atmosphere stretches far into space. When those gas particles drift close enough, Charon's gravity simply grabs them. No magnetic field needed, just a leaky planet and a nearby moon pulling the material away. Now, when the Apollo astronauts brought lunar soil to Earth, it was already loaded with hydrogen from the solar wind. The sun sprays the lunar surface with hydrogen, and over time, that hydrogen gets baked straight into the dust. That's the H, but you still need the O2 to create water. The regolith may already contain trace amounts of oxygen locked into minerals and dust, not as ice, but as something that can potentially be processed. It would mean that regolith is not just a nuisance that destroys gear and rovers. For a future lunar base, even small amounts matter. Water is heavy. Launching it from Earth is a nightmare. If the Moon can supply even part of what astronauts need, it could make a difference. Now, another cool side effect of this discovery is that drilling into the Moon could tell us more about Earth's history. You see, our planet is terrible at keeping records. It's like a giant recycling machine. It's always changing. Tectonic plates grind the crust down and melt it into magma. Winds and rains erode rocks. The air that we breathe now is different from the one that was around 2 billion years ago. Now, we can guess what the ancient atmosphere was like, but we don't have a physical sample. The Moon is the complete opposite. It's cold and static. When those Earth particles land on the Moon, they get buried under dust and stay there. They're trapped in the crystal lattice of the soil. Think of the lunar surface like an ice core in Antarctica. The deeper we dig, the further back in time we go. If we drill a core sample on the Moon, we might, theoretically, find layers of oxygen and nitrogen from 2.5 billion years ago. That is right around the Great Oxidation Event, when microbes first started pumping oxygen into our atmosphere. That could tell us something we don't know. It could prove that life started earlier than we thought. It could show us exactly how a dead planet turns into a living one. That's another answer you can give the next time somebody asks why we should go back to the Moon. Also define the green cheese. Hey, just Google it. You know, we've all begged for just 1 extra hour in the day. Actually, 2 hours would be better. Well, scientists have good news and bad news. The good news is that our planet is heading toward a future where a day could last 25 hours. The bad news is that eventually, the same physics that makes the day longer will also get rid of our planet's rotation, literally freezing Earth in time. Meaning endless days and nights and oceans fleeing to the poles, all while the atmosphere turns into a relentless planet-wide storm. Uh-oh. Now, back when the Earth was just a massive, messy cloud of dust and gas, gravity started pulling everything toward the center. As all that debris smashed together, it started to swirl, like water rushing down a drain, but on a cosmic scale. That spin caused a momentum. Since space is a vacuum, there was no air to slow us down. Earth just kept spinning, and that spin became a day. One full rotation takes about 24 hours, and that's the rhythm we've known since we started recording time. But the thing is, we adopted 24 hours as a close estimate. In truth, a day is never exactly 24 hours long. Now, basically, Earth keeps spinning, but it's constantly losing tiny bits of speed. That's mostly because mass keeps moving around. Think of it like a figure skater. If they pull their arms in, they speed up. If they put them out, they slow down. Earth does the same thing, except without arms. When the 2011 earthquake hit Japan, it shifted the ocean floor so violently that it pulled Earth's mass inward, instantly shorting our day by 1.8 microseconds. Conversely, as glaciers melt and water rushes from the poles to the equator, Earth's arms are spreading out, causing us to drag. We're not just sitting on a big rock. It's like we're on a wobbly spinning top that moves every time something heavy happens on it. Most days end up being a few milliseconds longer than 24 hours. We can't feel this, but atomic clocks can measure it. Over long periods of time, those milliseconds add up. And as they do, the length of a day slowly increases. That's how a 24-hour day starts drifting toward 25. To check this, scientists pulled together nearly 3,000 years of sky records. Thousands of years ago, people carefully recorded eclipses. It was a scary event. Kings, priests, and astronomers wrote the exact time and location when the sun vanished. Those records survived on clay tablets, scrolls, and manuscripts. For the sky to go dark, the sun, earth, and moon must line up perfectly. If the timing is off by even a second, the shadow falls on the wrong part of the world. Today, astronomers know the moon's movements with incredible precision. They actually bounce lasers off mirrors left on the lunar surface to measure its orbit. That's why, in theory, we should be able to rewind the past like in a YouTube video and see every ancient eclipse exactly where history records it. But when scientists tried that, the moon showed up too early, or too late. The shadow wasn't where the record said it should be. The puzzle only solves itself when you realize one thing: Earth used to be a little faster. When researchers adjust Earth's rotation to be slightly quicker, everything snaps into place. In other words, Earth was spinning a little faster in the past, and these eclipse records show it. On average, this translates to a day increasing by about 1 to 2 milliseconds every 100 years. That's 1,000th of a second. You'll never notice it. But over time, those tiny bits stack up. about a second every 10,000 years. That means we are roughly only 200 million years away from having that one additional hour of sleep. So the good news turns out to be only meaningful for future Earthlings. But why is this actually happening? Well, the answer is the moon. Its gravity grabs Earth's oceans and stretches them into huge tidal bulges. But because Earth spins much faster than the moon moves around us, those bulges don't sit neatly under the moon. They get dragged slightly ahead as the planet rotates. That means the oceans are constantly being dragged across the planet, rubbing against the seafloor and the continents. That rubbing creates friction, and friction is a thief. Where there's friction, there's heat. So the moon slowly turns Earth's spin into heat that spreads through the oceans and into space. And once that energy is gone, it's gone for good. Since there's no visible cosmic creature to push Earth back up to speed, day after day, the moon acts like a slow, steady brake, stretching our days little by little and drifting farther away as it does. Yes, as much as we used to fear that the moon would collide with Earth one day, it's actually going in the opposite direction. All that transfer of energy that's happening between Earth and the moon is slowly pushing our satellite further away, approximately 1.5 inches per year. We know this because during the Apollo missions, astronauts left mirrors on the moon's surface, and today scientists fire lasers at those mirrors and time how long it takes the light to come back. However, even though we are slowly pushing the moon away, don't panic. It's not packing its bags just yet. At the current rate, it would take tens of billions of years for the moon to retreat significantly. But it will stick around long enough to witness and maybe even cause the end of all ends, so to speak. The same braking force that is slowing us down now could eventually push Earth into a state called tidal locking. This has actually already happened to the moon. You know how we never see the dark side of the moon from Earth? Well, that's because Earth's gravity grabbed the moon eons ago and forced its rotation to stop relative to us. Well, if you give it enough time, the universe could return the favor. If Earth slows down enough to match its orbit around the Sun, the cycle of day and night will disappear. We could turn into what astronomers call an eyeball planet. Because the Sun would just hang motionless in the sky, the side facing it would turn into a blistering scorched desert. That's the pupil of the eye. The side facing away would freeze into a massive white shell of ice, the white of the eye. The only spot where life could hang on in this area is called the iris, a narrow strip caught between the crazy hot day and the frozen night. But even that wouldn't be a dream come true. You'd have super hot air on one side smashing into freezing air on the other. So this zone would be hit by insane hurricane-level winds whipping across the surface. Also, without Earth's spin shaping the oceans, water would slowly migrate away from the hot regions and collect in colder zones, reshaping coastlines and continents entirely. The planet wouldn't just have longer days. It wouldn't even look like Earth anymore. But here is the bright side. We will actually never see this happen. And neither will our descendants, at least not while watching from nearby. The math says it would take about 50 billion years for Earth to stop spinning and turn into that frozen eyeball fully. But our Sun doesn't have that kind of time. In about 5 billion years, the Sun will run out of fuel. It will expand into a red giant, swallowing the inner planets and likely vaporizing Earth entirely. Bye-bye! So, while Earth is slowing down, it will never actually get to zero. We won't end as a frozen, motionless rock. We'll end as we started, space dust. By the time Earth ever stops spinning, humans certainly won't be watching from the solar system. We might be scattered across the galaxy, living in space, or not even human anymore. Some of us could live inside massive structures built around stars, capturing their energy instead of orbiting them. Others might drift near black holes, using their gravity and energy in ways we barely understand today. Entire civilizations could exist as uploaded minds, connected through a galaxy-wide network, living in simulations instead of physical worlds. Well, wherever we are, Earth would just be an old planet concluding its story. For the last few decades, Earth has had an interesting coincidence. The northern and southern hemispheres have reflected almost the same exact amount of sunlight back into space, but new data from NASA shows that this symmetry is collapsing. The planet is becoming lopsided in a way we haven't measured before. Why is this happening? And will it change the weather we rely on? Well, let's talk about that. If you tear the map in half at the equator, you get two drastically different pieces. The northern hemisphere is the crowded side, having around 68% of Earth's landmass. It has massive continents of North America, Europe, and Asia, the sands of the Sahara, and the snows of the Himalayas. The southern hemisphere is the complete opposite. It is a water world. Aside from Antarctica and a slice of South America, it is almost entirely a deep, dark ocean. In fact, there's a spot in the South Pacific where you can travel for thousands of miles without hitting a single patch of dirt. This area is home to the oceanic pole of inaccessibility, better known as Point Nemo. It's so remote that if you sailed there, the nearest humans wouldn't be in Chile or New Zealand. They'd often be the astronauts on the International Space Station passing overhead. It's one of the emptiest places on Earth, surrounded by thousands of miles of open ocean. Now, when sunlight travels 93 million miles and hits Earth, two things can happen. It either bounces off the planet and escapes to space, or it gets absorbed. That's because of the phenomenon called albedo. It works exactly like your wardrobe on a scorching day. Lighter surfaces act like mirrors, bouncing the sun away to keep you cool. Darker surfaces are like sponges. They soak up that energy and turn it into heat. Now, humans have actually figured this out on a smaller scale. If you didn't know, many traditional houses on the Greek islands are painted bright white. It's like a form of ancient air conditioning. The white paint reflects the intense Mediterranean sun and helps keep the inside cool. Cities are now trying a similar trick. Places like Los Angeles have spent millions of dollars coating black asphalt streets with a special gray surface to boost the city's albedo. By making the ground a lighter color, street surfaces can cool by about 15 degrees. Now, on a much bigger scale, planetary even, ice, snow, and bright deserts act like mirrors, bouncing back the light, while oceans are the opposite. They soak up the rays and store that energy as heat. So, according to physics, the land-heavy north should reflect more sunlight. The ocean-heavy south should absorb more. Meanwhile, when looking at Earth from space, one half should look brighter than the other. So for decades, NASA has tracked Earth's energy using a system called CERES, short for Clouds in the Earth's Radiant Energy System. These satellites measure how much sunlight arrives and how much leaves. This is how we learn that Earth is cheating around the albedo rule. Now, think of Earth's atmosphere as a giant planetary mixer, constantly pushing heat between the north and south to keep it from piling up in one place. According to the latest data, that mixer is starting to fall behind. When scientists looked closely at the CERES data, they saw a clear split forming between the hemispheres. The northern hemisphere is now holding onto more of the sun's energy than the southern hemisphere. Specifically, the north is gaining about 0.3 watts per square foot per decade more solar energy than the south. Yep, that sounds microscopic, but multiply that by every square foot of the Earth's surface, and you have a massive engine of heat that could make the weather unpredictable. Now, you would expect clouds to push back by reflecting more heat to space. But the data shows that the response hasn't been strong enough, so the extra energy keeps piling up in the northern hemisphere. Now, this is a big deal because heat is what makes the weather move. Hot air rises and pushes wind and storms around the globe. If one side of the planet creates more pressure than the other, those wind patterns have to shift. So it's not just that the weather is getting hotter, it's that it physically moves to new places. You've probably heard of the geographic equator, the invisible line running around the middle of the planet. But there is another equator related to weather. It's called the thermal equator. Think of this as a giant collision zone. Imagine pointing two powerful fans at each other. Where the airstreams meet, the air often gets forced upward, building what could look like a moving wall of rain. Scientists call this zone the Intertropical Convergence Zone, or ITCZ. It marks the planet's thermal equator. Sailors had a better name and knew it as the doldrums. They knew it as a zone where winds cancel each other out. Pirates in the 1700s were terrified of it. You could get stuck there for weeks, just floating, waiting for your drinking water to run out. The system acts like a planetary thermostat. It likes to hang out where the heat is. For most of human history, it stayed right in the middle. But if this imbalance keeps growing, it could nudge the thermal equator north over time. Now, you might be thinking, so what if the rain belt shifts a few hundred miles? Well, history gives us a pretty striking example. About 6,000 years ago, this rain belt sat farther north than it does today. At the time, much of what we now call the Sahara wasn't desert at all. It supported lakes, grasslands, wildlife like hippos and giraffes, and thriving human communities. Rock art from the region even shows boats and swimming scenes. As Earth's orbit slowly changed, the rain belt migrated south. Over time, rainfall faded, lakes dried up, and the landscape transformed into the Sahara we know today. The trigger was different, but the mechanism was the same. When the planet's energy balance shifts, the thermal equator moves, and the rain moves with it. This is a huge deal because rain is incredibly important for food production. It waters the regions that grow our coffee, our chocolate, not our chocolate, yep, and the crops that billions of people eat. If that belt chases the heat and moves north, the rain goes with it. The jungles in the south could dry out, while cities in the north would get hit with floods they were never built to handle. But the air is only half the story. Down at lower elevations, the extra heat triggers a chain reaction. Remember the t-shirt analogy? Much of the northern hemisphere depends on bright snow and sea ice to reflect sunlight away. But as temperatures rise, that low-altitude ice melts. When the white surface disappears, it exposes darker ocean water or bare ground underneath. This creates what scientists call a feedback loop. As the ice melts, it reveals the darker ocean or land underneath, and that dark ground absorbs more heat, which can cause even more ice to melt. It's a cycle that could make it progressively harder for the region to cool itself down naturally. Meanwhile, the oceans take their time responding. Global currents act like a giant conveyor belt, moving warm water around the globe to balance energy. But this system is delicate. It only works when the water's temperature and saltiness are just right. When the north hoards too much heat, it throws the currents off. And if the belt slows or reroutes, the effects don't hit overnight. They unfold gradually over decades or even centuries. But finally, is this just a temporary glitch? Or is the Earth settling into a brand new pattern? Right now, scientists can't tell for sure. Maybe the clouds will finally show up and fix the balance. Maybe the oceans will move the heat around and save the day. But if the North keeps gaining an energy advantage, the weather maps we rely on might change for decades or centuries. If that's the case, many places will have to rethink their daily life. Those not used to rain would suddenly feel cheated, while the value of raincoats, umbrellas, and white t-shirts skyrockets.
It's official. Official. A day will no longer last 24 hours. Earth's now spinning faster, literally, and our days are going to get shorter. At the moment, it's believed that the shortest day happened on July 10th, 2025. It was shorter not by much, just a fraction of a second. 1.36 milliseconds according to most sources, but still. And all because of the moon's position messing with Earth's rotation, just enough to speed things up. If it turns out to be not a one-time thing and Earth keeps spinning faster, it could be the start of a big mess. All our time stuff like GPS, the internet, atomic clocks, even how countries keep time, depends on the day being 24 hours. But if the planet speeds up, those systems could totally freak out. clocks would get all out of whack, and anything that needs perfect timing could go sideways. We're talking about more than just a few lost seconds. This could shake up everything. Flights, money transfers, basically how we live day to day. We'll have to rethink how we measure time. Are you ready for that kind of chaos? Now, normally a day is 24 hours, or 86,400 seconds, because that's how long it takes for the planet to do a full spin. But Earth's rotation isn't always stable. A bunch of things influence it, like where the sun and the moon are, or how the planet's mass is balanced. Earth is like a giant spinning top, and anything can throw it off rhythm. But our planet has been slowing down for a long, really long time. Because according to scientists, about 1 to 2 billion years ago, a day only lasted 19 hours. Not because the planet was lazy or anything. Nope, it was the moon's fault. It was way closer to us back then. Its gravity had a stronger pull, and that made Earth spin faster. And that faster spin meant shorter days. The thing is, the moon is slowly drifting away from Earth, and as it does, Earth's rotation slows down, and our days get longer over time. But during that billion-year window, something weird happened. The moon kinda just hovered at a certain distance. It wasn't moving out, it wasn't pulling harder. It was like it paused. And that pause locked us into 19-hour days for what scientists are now calling a boring billion. It was a time when pretty much everything on Earth slowed down. Tectonic activity was stable, the climate wasn't doing anything weird, and even life kind of plateaued. Now, let's get into the sciencey part. The moon's gravity controls our ocean tides. That's what slows down Earth's spin. But the sun pulls on Earth too, just in a different way. When sunlight hits Earth's surface and heats it up, that creates what's called solar atmospheric tides, and those can actually speed up Earth's rotation. Right now, the moon's gravitational tides are about twice as strong as the sun's atmospheric tides, which means the moon is in charge when it comes to Earth's spin. But back in the boring billion, the sun and moon were basically in a tug-of-war with equal strength. This phenomenon is called tidal resonance. It's like Earth hit a cosmic pause button. If the moon hadn't backed off, we might still be living in a 19-hour day world right now. These days, the moon is still drifting away from us, and because of that, our days are slowly getting longer. Until lately, things have gotten weird. In the last few years, scientists noticed that Earth hasn't been sticking to schedule. In fact, it's been spinning faster, and I mean record-breaking fast. Back in 2020, Earth started picking up the pace more than it had since scientists started clocking it in the 70s. Then came July 5th, 2024, the shortest day ever recorded. We lost 1.66 milliseconds. Not a big deal if you're just watching videos on YouTube, but on a planetary scale, it's kinda huge. Now, we get back to July 10th, 2025. On that date, the moon was sitting way up near the poles, very far from Earth's equator. And that changed the game. When the moon is hanging out closer to the poles, it messes with Earth's rotation and makes our days a little bit shorter. That kind of change isn't unusual. Earth's spin has always had some ups and downs. But today, the moon isn't the only factor. According to NASA, human activity is changing how Earth spins too. Between 2000 and 2018, moving ice and pumping groundwater around the planet shifted enough mass that it added 1.33 milliseconds to our days per century. Natural disasters can mess things up too. Remember the massive earthquake that hit Japan in 2011? It actually shortened Earth's day by 1.8 microseconds. Just one quake, one microjolt to the planet's schedule, but the consequences were catastrophic. On March 11, 2011, at exactly 2:46 p.m. local time, a huge earthquake hit off Japan's east coast. We're talking magnitude 9, one of the biggest quakes ever recorded. The epicenter was about 80 miles from Sendai and over 230 miles from Tokyo. Japan's main island shifted 8 feet. Yes, the ground moved and whole cities literally slid. But it didn't just shake buildings and trigger a tsunami. The quake was so strong it redistributed Earth's mass, like shifting weights around on a spinning top. When you do that, the top spins differently. Same deal with Earth. The movement of tectonic plates was enough to tweak the whole planet's rotation. The thing is, the earthquake moved land and shifted Earth's figure axis. That's the axis our planet's mass balances around, by 6.5 inches. That's separate from the north-south spin axis, which we rotate on daily at about 1,000 miles per hour. But still, that shift was enough to make Earth wobble differently as it was spinning. It didn't tilt the entire axis in space. Only stuff like the sun or moon's gravity can do that. But it was still a major shakeup, no pun intended. And it wasn't the first time this had happened. The 2004 Sumatra quake, a staggering magnitude 9.1, sped up Earth's spin and cut 6.8 microseconds off the day. Chile's 2010 quake took off another 1.26 microseconds. Every time one of these mega quakes hit, it's like Earth gets a tiny jolt, spinning just a hair faster. And it might not be over. For example, that March 11 quake unleashed more than 80 aftershocks that were magnitude 6.0 or higher. Long after, some of those aftershocks were still tweaking the day length. It was very subtle, changes in millionths of a second, but real. But the thing is, even the seasons can mess with how fast Earth spins. A geophysicist from the University of Liverpool has explained it like this. There's way more land in the northern hemisphere than in the south. So, during northern summer, trees grow leaves, and that leaf mass moves upward, farther from Earth's center. And it sounds pretty harmless, right? But no, that tiny shift actually slows down our planet's spin, just a bit. Think about a figure skater arms in, they spin faster. Arms out, they slow down. Same with Earth. When its mass shifts away from the core, it rotates more slowly. So yeah, in the summer, Earth literally chills a bit, spin-wise. Now you don't panic about your day suddenly feeling longer yet. Your clock is still gonna say 24 hours. That's just how our timekeeping works. As for these differences, they're milliseconds. You'd never feel it. But the problem is that over time, it all adds up. If the planet ever spun slow enough that we were off by more than 0.9 seconds, then we'd have to do something. That's when the International Earth Rotation and Reference System Service steps in. These are the people who keep tabs on Earth's spin, and if things drift too far out of sync with our clocks, they throw in a leap second to fix it. Yep, they literally add a second to the clock every now and then to keep Earth time on track. It's like the universe's version of a software update. In any case, with the moon slowly drifting away and Earth calming down, the fact that our planet is suddenly picking up speed, even just a little, makes experts and ordinary people raise their eyebrows. It's a reminder that even something as basic as a day isn't set in stone. The planet's moving quicker. Time is literally slipping. Something's shifting.